thank you very much to the organizers for this opportunity. I have to say that this has been a very interesting meeting for me. And I also have to acknowledge that the organization has been very nice. I mean, I didn't know this platform of Meterway, but it's really quite remarkable to make it slightly better now that we are at the distance. In any case, I wanted to talk to you about semi-classical gravity. So again, a touch on the gravitational side of these mixed quantum and classical systems. So as Jonathan has emphasized in his talk, there are indeed some conceptual, perhaps, problems with semi-classical gravity, and we shouldn't. My view is that we shouldn't take it as the end theory or something that we think is completely fundamental, but rather as an effective description of either something coming from quantum gravity or some more special way of coupling perhaps classical gravity to quantum fields, such as the one described, well, such as, I mean, not really described, but argued for in the previous talk. So in my talk, I want to focus on the situation of considering semi-classical gravity as a theory in its own right, and as such a theory that should be examined carefully mathematically, and that we should understand its properties a little bit more a little bit better. So in particular, I'll be focusing on the initial value formulation of semi-classical gravity. This is known to be a rather hard problem, but I will present some motivations why this is interesting. And because the initial value formulation of the theory is so hard, I want to at least make progress in some simplified situations, such as static spacetimes. And I will then show you how what you can learn from working in the static spacetime can be extrapolated, at least in some special cases, to non-static spacetimes. And I think this is really exciting. So my talk will be semi-classical gravity, its initial value formulation, and in particular some special cases, you know. Okay, so let's start. I'll give a more detailed motivation in the next couple of slides, and then I will spend quite a bit of time talking about semi-classical gravity, because I think that it would be interesting for the audience to look at the details of that theory and look not only at the conceptual complications of it, but also at the mathematical difficulties in working with it. I will then specify two static spacetimes, and in that context, you can really say a lot more, and you can really talk in terms of the initial value problem. And then I will talk about how to relax staticity and still obtain some well-posedness results. So this bit where I relax staticity, this is some work in progress I'm doing that we have under control with a colleague of mine, but that has not yet been published, and that we still have to put the dots on the i's, because we really want to present it as theorems rather than just some vague discussion. And then then I'll just continue with some final remarks. Okay, so the motivation. So why semi-classical gravity? Well, for people like me coming from, let's say, the high energy physics kind of quantum field theory community, we think that presumably semi-classical gravity is the semi-classical limit of a theory of quantum gravity. But of course, as we have discussed here many times, and as I think also some people in foundations of physics are considering, gravity could be fundamentally classical. Then, you know, all the more relevant to consider this kind of systems in at least some particular regimes where we know that semi-classical gravity should be an approximation to something else. So what those regimes are, I will not, give many details, but I think that more or less in the quantum field theory community or quantum field theory in curved spacetime communities, there is a certain intuition as to if your states are not, completely wild superpositions of massive, very large objects like the moon, for example, as in the previous talk was discussed, and you are very far away from, Planck energy in the particular scale that you're interested in, then presumably semi-classical gravity is interesting. It is a natural extension, and it is indeed a strong motivation for doing quantum field theory in curved spacetime. So indeed, a lot of energy has been devoted to defining, for example, the renormalized expectation value of the renormalized stress energy tensor, which is a fundamental object in semi-classical gravity. And we believe it to, be important in situations where gravity and quantum effects are relevant. And of course, in the early universe, so perhaps during inflationary phase, this framework should be relevant, and of course in black hole physics. So just to mention one of the very important open puzzles in theoretical physics, the black hole evaporation and information loss, is stated as a semi-classical gravity problem. It has to do with the back reaction of quantum fields on black hole geometry and how that leads to the evaporation of a black hole. So this process is poorly understood. At least there's general consensus that there is no solution yet to this problem. So indeed, another motivation to get a better understanding of semi-classical gravity. Well, nevertheless, there are some difficulties. It's a fourth order problem in the space-time metric, unlike the Einstein equations that are second order PDE system for the metric. The renormalization of the stress energy tensor, while you solve the dynamical equations, it poses a lot of difficulties to even stating proper initial data for the system. And this is because the way that we usually understand renormalization in curved spacetimes is in a covariance setting, so having to do with a solution in all spacetime. But and then we give some conditions on how that covariant object should look like. But if you don't have the covariant object because you're trying to solve for it, then you have to give conditions on initial data, and this is very hard. Okay, so the quantum state is non-local, so somehow non-locality plays in these equations. And just in short, it's a complicated problem even for the free Klein-Gordon field in the matter sector. So for me, studying the initial value problem is motivated by the fact that, as I have said, semi-classical gravity should be good in some regime, and hopefully in this regime it can be used to make predictions. The initial value problem, I think, is the correct way of understanding causality, which we would like to have in any physical theory in one way or another. Okay, and just in general, I would like to understand better the mathematical properties of semi-classical gravity. So why static spacetimes? Because full semi-classical gravity is very hard. So we can get a lot of experience by working with these symmetry reduced problems. Furthermore, if we have non-static spacetimes with static regions, it can be interesting to understand how to prescribe good initial data in static spacetimes. Moreover, in static spacetimes, we have some of the most interesting states. So it is in static spacetimes where we have vacuum states, such as the Minkowski vacuum, and thermal equilibrium states, so at finite temperature. And one can learn lessons by doing this. So I'll spend some time talking about semi-classical gravity from a very general point of view. So consider the semi-classical gravity equations with a Klein-Gordon field. They are semi-classical in the sense one of steep Fulling stock, where he also talked about semi-classical in another different sense, which is not this one. And so the semi-classical gravity equations are the equations one. So let's look at them in more detail. So in the first equation on the left-hand side, we have geometric quantities. So there's a capital GAB and a GAB. GAB is what we call the space-time metric in general relativity or in gravity more generally. And capital GAB is just equal to a combination of something that we call curvature tensors in gravitational physics. So curvature tensors, so the first one, so you see on the third bullet, can you see maybe you can see my mouse, I'm pointing at it here. Okay, so this is known as the Einstein tensor, and it's built out of two objects. So the Ricci tensor, which is a contraction of the Riemann tensor, which fully characterizes the curvature in a space-time or in a manifold, and its trace, which is called the Ricci scalar. So it's just a combination of those two curvatures. It is second order in the metric, and it is also covariantly conserved. Okay. So this lambda here is just a cosmological constant term. This is standard in GR as well to include such a term. Okay, on the right-hand side, this is sourced in semi-classical gravity by a term, it's coupled to a term through Newton's constant, and is sourced by the expectation value of the stress energy tensor of a field in some state omega. So here I take the convention that by states, I mean states in the algebraic sense. So I just mean expectation values of objects. Okay, so this is different to thinking directly in terms of Hilbert spaces, but I'm just thinking of expectation values as defining states. Okay. Then on the second line, you have the Klein-Gordon equation. Okay, so that's the D'Alembert, a mass term, and this is you allow yourself to couple to curvature with some real parameter, and that parameter is called the curvature coupling. So in this case, I will be restricting myself to a free Klein-Gordon field, which could have mass and an arbitrary curvature coupling. Okay, for the moment. So if there's any questions, feel free to ask. So as you can see in this on this slide, I've written all geometric objects in red and all quantum objects in blue, and the expectation value of the stress energy tensor is purple because it has a little bit of both. And I will now focus on this term because it is really what is more complicated about semi-classical gravity. Okay, so as I said, by a state, I mean something that is defined by its endpoint functions, as in equation 2. So here, phi of f, by phi of fi, I simply mean suitably smeared fields. So I am thinking of fields as distributions with values. If I have a concrete representation with values in operators on Hilbert space, or if I'm more abstract, these are algebra value distributions. So since these are expectation values, for the moment, I can just take it to be the more general algebra value distributions. This is not a problem because if I consider it to be like that, then I can then perform the GNS construction and obtain a complete representation. Okay. So the state must satisfy a couple of things. It must be normalized and be positive. Okay, these are just general properties that you demand of the state. I will henceforth consider that the state is a quasi-free state. This simply means that all the endpoint functions can be defined in terms of the 2-point functions. And there's a little formula for doing that, which is equation 3. It's not, the details are not important. You should just keep in mind that from now on, whenever I say a state, I just mean the 2-point function so the 2-point function completely defines the state in my setting. So in practice, the 2-point function is given by equation 4. So I just see it here is mirrored against two test functions that are the test functions of these two fields. Of course, then I can see that 2-point functions by distribution, and it has a distributional kernel. Excuse me. It has a distributional kernel, and this is nothing but the Weidmann function that we learn about in all our textbooks. Oops, how do I minimize this? Like that, okay. That we learn about in all our textbooks. And the Weidmann function is really how I'm gonna characterize the state, okay? So the Weidmann function is a distributional bisolution to the Klein-Gordon equation, as I show in this equation as well. So in practice, in semi-classical gravity, it's often convenient to trade the equation on the field for two equations on the Weidmann function, and this is something that we will do. Okay, so for defining the stress energy tensor as well, its expectation value, we would like to do things like, for instance, take the coincidence limit of two covariant derivatives of the Weidmann function. But of course, this diverges. I mean, we know this already from Minkowski spacetime, that it diverges in the coincidence limit when we evaluate the 2-point function at the same point, the Weidmann function at the same point. However, it diverges in a way that we know how to control if we have worked on quantum field theory in curved spacetime. So in curved spacetime, we know that for free theories, good states have a precise characterization of the distributional singularities, which is this. If this, well, there is a class of states that for which we know how to control the singularities because they diverge in a precise state, and these states satisfy something called the Hadamard condition. So a state is Hadamard if in something that we call a convex normal neighborhood. That just means that it's a neighborhood for which, for any 2 points, any geodesic connecting those 2 points is fully contained in the neighborhood and is unique. So you can just think as a small diamond in spacetime. So a state is Hadamard if in a convex normal neighborhood, so for two sufficiently close points, it behaves like this equation. So it has 3 terms, as you can see. So let's go term by term. The first term in the numerator has a bifunction, which is actually smooth, called the Van Vleck-Moret determinant. It's smooth if the metric smooth, and it's called the Van Vleck-Moret determinant. It's fully depending on the geometry only, and well, what is important is that we know it completely if we know the geometry of spacetime, and it's smooth. Okay. And the denominator, what we have here is an object called Singe's world function, which is 1/2 of the square of the geodesic distance between 2 points. So this epsilon here is just a regulator of the kind that we use in quantum field theory, because this is a distribution. So we have to prescribe how to go around the singularity, if you will. Okay, the second term has a logarithmic term. Okay, so here this coefficient in front of the logarithm again is smooth and it's symmetric. By the way, this one as well, it is symmetric, the Van Vleck-Moret determinant. And the final piece is and yet another smooth symmetric coefficient. Okay. I have to say this L squared is just an arbitrary length scale. Varying this length scale is kind of running in the renormalization scale. Okay, so what is important here is that, what is important here is that the appearance of distributional singularity. So if you see, they come as 1/sigma and then a logarithmic singularity in sigma. So the singularities that appear in the coincidence limit when x prime goes to x appear in these 2 terms, whereas the third term, so in the first 2 terms, whereas in the first term is singularity free. So for all Hadamard states, the singularities are universal because these 2 terms only depend on spacetime geometry and they don't depend on the details of the state. The details of the state appear only in this W coefficient. So just to, yes?
10 minutes to go.
5 minutes.
10 minutes, including questions.
10 minutes. Thank you very much. Okay. Okay, so just to be a little bit more precise, this coefficient V, we know how to obtain it via something called the Hadamard recursion relations or some expansions in geodesic distance. And similar expansions hold for W, but W is W0 encodes state dependence, so it's not completely freely set from these recursion relations that can be obtained from these series expansions. Okay, so these first two terms together have the exact form as something called the Hadamard by distribution of the Klein-Gordon operator. So it's a fully geometric object that will depend only on space-time geometry and these two parameters, the mass of the field and the curvature coupling. So the distributional singularities of the two-point function, as I said, are state dependent. This means that we can subtract the singularities in a unified renormalization prescription that is covariant. And the renormalization prescription will be the same for all Hadamard states because the singularities are state independent. And indeed, this is what we do. So before computing these interesting coincidence limits that we need to intuitively define the stress energy tensor, we take the two-point function, the Weidmann function, we subtract the singular structure, and then we apply this operator that takes derivatives in the points x and x prime, and that multiplies, suitably by the mass. And this is nothing but a point-splitted version of the classical operator that you would use to act on the classical stress energy tensor. So if this were a classical field and you took this limit, this would be the classical stress energy tensor defined by a point splitting. So here, remove singularities, apply this point splitted operator, and take the limit. Okay. Now there's a little problem here. If you just do that, this object is not covariantly conserved, so the equations make no sense. But we know how to fix that. In fact, there is a more elegant way of fixing that without introducing this term by hand, but I don't want to go into details. Let me for now say that we know that the correct term that we need to add is this V1 term. So as you can see, this term is higher order in metric derivatives because it contains a term that goes like box R. So this is fourth order. And this is why the semiclassical gravity equations are higher order equations. There's a final term which has to do with renormalization ambiguities. So you can basically add any symmetric covariantly conserved term that only depends on the geometry to this expression. And this is kind of the classification of the terms that you can add, and they are also typically of higher order. But even if you wanted to set that to 0, which you can't because there will always be these ambiguities in renormalization, you already have a higher order problem here. Okay, to summarize, semiclassical gravity is given by equation 5. You have some equation for the space-time given by this prescription for stress energy renormalization, and then equations on the two-point function. So because this is fourth order, you would like to give metric initial data in the form of 3 normal derivatives of initial data, and well, that's 4 pieces of initial data because you have a fourth order problem. And for the matter initial data, what do we have for solving these equations for the two-point function? What we have is the correlation functions between 3 fields on the initial surface, a field and momentum, and momentum correlations. Okay, so of course these initial data should satisfy the canonical commutation relations. Okay, and you will have further data if the one-point function is not 0, but let me just for the moment ignore that case. So let's examine the problem in the ultrastatic case. In ultrastatic spacetimes, the metric takes this local form. That is almost the definition of an ultrastatic spacetime, that you can find a coordinate system in which the metric looks just like this. In front of this dt squared coefficient is just -1, and then you have a spatial metric for the spatial part of the metric. So this is a block diagonal, if you will, description of the metric. Okay, so this ultrastatic spacetimes, of course, they have a distinguished notion of time, which is given by this t coordinate that is nothing but the integral curves that some time like surface orthogonal killing vector field. Okay, where the surfaces are defined by t equals constant. Okay. So in ultrastatic spacetimes, actually working with geometry is very easy because the Riemann tensor, which characterizes the spacetime curvature, can be described in terms of the Riemann 3 tensor of the 3 geometry of this metric H, the spatial metric, and similarly for the Ricci scalar and Ricci tensor, and I'm denoting them by this curly R, okay, or calligraphic, if you will, R. Okay. So in ultrastatic spacetimes, the Einstein semi-classical gravity equations take the form of equation 8a to 8c. They take a complicated form, but just bear in mind that on the initial surface, these are just constraint equations. Okay, and this is what makes the ultrastatic case and the static case so easy to work with. Moreover, equation 9 in the ultrastatic case simply becomes what we call an abstract wave equation. Okay, so this is an elliptic operator, and here you have second derivative in time. Okay, so this elliptic operator is, of course, having to do with the Laplacian of the three metric and then some potential term. Okay, so the point is that we must be able to prescribe initial data such that these constraints hold on the initial surface, and then we want to see that those constraints are preserved. So imposing constraint conservation, and I give more details in my paper, implies that states must be time translation invariant. And then one can try to solve for time translation invariance states in this setting, which are the ones that are going to satisfy the constraints at all times. So I'm going to assume that this elliptic operator is positive. And then if it is positive, there are some general results from K from the 70s that they say that this operator is essentially self-adjoint. This means that it has a unique self-adjoint extension, and this allows me to use functional calculus to obtain the solutions. So given some initial data, I can obtain the solutions to this abstract wave equation as the last equation on this slide. Okay, so given some correlations prescribed as initial data, I can obtain the solution. Okay. Moreover, if I impose time translation invariance, which guarantees constraint conservation, then the initial data must be of this form. So it's highly constrained. So this datum for the correlations of the three fields with itself are free, but then the momentum correlations and the momentum field correlations are completely constrained. Anyway, in this case, solutions take this form. There are, of course, some familiar examples of time translation invariant states. So, for example, vacuum states. For them, you prescribe this kind of initial data for the initial correlation fields. Okay, so just in spectral functional calculus language is very simple. And then you get indeed the familiar vacuum state solution. So this psi are nothing but the eigenfunctions of that elliptic operator. Okay. So in static spacetime, the key idea is to bring static spacetime to ultrastatic spacetimes by a conformal transformation. You can always do this, and this conformal transformation will be time independent. So then you can solve the problem in the ultrastatic case and transform back to the static spacetime to get solutions in that situation as well. Okay, so relaxing staticity. So this is work in progress with Sujoy Modak, who is in Universidad de Colima in Mexico. Okay, so consider semiclassical gravity and globally hyperbolic spacetime. You have a fixed static metric in the background, and then you allow yourself to multiply it by a conformal factor that is spacetime dependent. And you want to find this metric. So this is the dynamical geometrical object that you're interested in. So that, of course, means you want to find the conformal factor out of initial data. So semiclassical gravity equations are now a fourth order equation for the conformal factor, the Klein-Gordon equation for the two-point function, and some constraints. If you assume the field is conformally coupled, then you can bring the Klein-Gordon equation and solve it also by conformal techniques. I will not give the details, but just...
The time is up, so if you could try to wrap it up.
Okay, this is my last technical slide, and then I just conclude. Bring it to a simpler problem and solve it there. And then we know how to solve the rest of the equations using Liray's theorem. so we can bring them to this fourth order problem to a diagonal quasi-linear hyperbolic PDE system and then use Lie-Ray's theorem to obtain well-posedness. Okay. So there are some open questions. Well, are there really explicit examples? What is the role of, for example, something like state collapse in this theory? It will violate them. And okay, we would really like to extend beyond these examples. Okay, so could we describe the classical metric, for example, a la Koopman, and find other ways of coupling the classical spacetime structures to quantum fields? This would, of course, require something like Koopman field theories, and I guess we have more results, and here's a preprint if you want to have a look at it, and that's it. Thank you.
Thank you very much for the talk. Maybe one quick question, if there's anyone. If not, maybe I'll just make one quick remark about the motivation part. Appeared here as well as in the previous talk about the black hole radiation and information paradox.
Yeah.
I mean, it's not clear to me why this is so special about gravity. I mean, if you just take the simple Ising magnet at low temperature, where all the spins are pointing up, if you heat the magnet and cool it down again, you have a lot of information and curvature singularity in the state space. Or if you have quantum phase transition, where you have a degenerate eigenvalues of the Hamiltonian, then you get lots of information. So it seems the phenomena is fairly universal, and it has to do with the degenerate eigenvalues of order parameter or Hamiltonian. And certainly it's known in statistical physics for a long time that that's what one has. So it's not clear to me whether gravitational effect is unique in this regard to motivate that particular issue.
Okay, just 2 comments. I think that in these examples that you are describing, I mean, one comment is on a technical nature, the other one is less technical. Perhaps on the technical nature, first of all, I think when we describe the information loss puzzle, we are never talking about Hamiltonians or things like that, because Hamiltonians is not a concept that is well defined in general curve spacetimes. So I think the origin of the information loss is of a different nature here. The second point that is a bit less technical has to do with the fact that perhaps these models like Ising model and so on, we can think of them as effective ways of describing a system. Whereas I think in the information loss puzzle, we would like to think that this is really a fundamental system. There is nothing being effectively described here. The phenomenon is completely independent of what quantum field theory you put on space-time to describe how black holes evaporate. And on the gravity side, we would like to believe that we can describe gravity fairly well for black holes when we are in the exterior region, and we can see how they evaporate. The problem in that setting in black hole information loss puzzle is that we really don't know the endpoint of evaporation, because this requires us to really diverge in a way from the comfort zone of general relativity. So I think it is fundamentally distinct.
Thank you. Maybe just very quick 2 questions. So Andrea and Jonathan.
Mm-hmm.
Yes, can you go to your slide 7, I guess?
Yeah.
Yeah, how does the Moret-Van Vleck determinant comes about there? Isn't that related to some transformation of coordinates?
Not really. I mean, how it comes about is okay. How it comes about is that really this coefficient a priori, you don't know what it is. Okay. So I've already said that this is a Van Vleck-Moret determinant, but this is actually a result coming from the following fact. How you obtain these coefficients is, as I said, through this Hadamard recursion relation. So you give a covariant at least in analytic spacetimes, this is rigorous, okay? You give a covariant expansion in terms of geodesic distance for this coefficient. So this is typically called U in much of the literature as well. And this allows you to recursively solve what these coefficients are. And if you solve those recursion relations, this turns out to be the square root of the Dambach-Moret determinant. This is where it comes from.
Okay.
Okay. So it is a result that is obtained from this. And by the way, these recursion relations are just, you insert this ansatz and you demand that the 2-point function is a solution to the Klein-Gordon equation. So this is what gives you the recursion, okay, from the ansatz. Then you solve it order by order. Okay.
Two quick questions. One, you said in your answer previously that in GR there's not a well-defined Hamiltonian. And I agree with you, there's not a well-defined local energy, but why can't we consider the ADM Hamiltonian to be the Hamiltonian?
We can. I mean, it's just trivial.
You mean when the constraint is satisfied at 0, but it's still
and
the dynamics.
Exactly, and the constraint is satisfied on solutions, right?
Yeah.
So then it's trivial. But more generally, even if you just do quantum field theory in curved spacetimes, you don't have these kind of Hamiltonian methods to, in general. I mean, of course, in ultrastatic spacetimes you do.
Why isn't the ADM formulation a good Hamiltonian formulation of general relativity?
Of general relativity?
Yeah.
No, I think for general relativity you can do ADM formalism. There's no problem with that.
And then
I'm just saying, yeah.
Oh, and yes, I guess the second question is that the elephant in the room with these semi-classical methods is that you're sourcing the gravitational field with the expectation value.
Yes.
And
yes, of course.
How are you dealing with that here?
Okay, so this whole presentation and what these papers are about is really about understanding the mathematics of this system. As I said in my motivation, I do not consider semi-classical gravity to be fundamental. There are, of course, ways of bringing semi-classical gravity closer to a fundamental level. For example, if you include state collapse in something like dynamical state collapse theories, then you could say you're never going to move out, or you're never going to get these really exotic moon superpositions where the theory is completely off, because simply collapses will prevent that from happening. And you will always remain in the semi-classical gravity regime unless you go to very high energy.
But I mean, even if I have collapse and I have the moon has now only a 50% chance of being here and a 50% chance of being here, you still have the problem that the expectation value, the stress energy tensor looks like, marbles will roll towards the center and it looks like you have two halves. So sorry, the point. Why should we trust this at any level, or at any level where it becomes interesting, where we're interested in it, where we do have fluctuations, then it seems that we can't trust it at that point.
Yeah, sorry, the point with collapse was exactly that collapse will prevent these macroscopic superpositions in the same way that it prevents, ideally for what it has been designed, it prevents the superposition of chairs.
But it doesn't prevent statistical mixture. So you still will have a statistical mixture, a classical mixture of the moon having a 50% chance of being here and a 50% probability of being here. So it's not a superposition, it's just a classical mixture. And then you have the problem.
I think semi-classical gravity doesn't deal with statistical mixtures. It deals with quantum systems. I mean, a classical statistical mixture is not something that you would describe, that there's no, if you will, there's no problem. You simply have a mixture of solutions. I mean, if the moon is here, then this is the gravitational field. I use Einstein field equations. If the moon is there, then I use Einstein field equations and I have another gravitational configuration. This is completely different setting in my view.
So one final very quick remark by Stephen, and then we move on, please.
Okay.
I think that at one point earlier in your slides, you had a cosmological constant. Is that right? Did you keep it in the final equations? I didn't see it. The point I'm trying to make is that on physical grounds, one would expect that it would be very hard to find any consistent solutions of this problem you've posed, because the quantized matter is going to produce energy that's going to cause the universe to collapse. So you wouldn't expect to have a static solution unless you have a cosmological constant of the proper sign to stop the collapse. Am I missing something?
Well, I mean, there is a static solution that has no cosmological constant, and that's the Minkowski vacuum in Minkowski spacetime.
Yes.
Whether that's stable is perhaps a different story, which I wouldn't put my money on claiming something there.